Hello. We're going to start moving in the class towards a discussion of biochemical pathways. And we're going to see that the reactions that are occurring in these pathways are similar to the reactions that we've been seeing this semester: nucleophilic addition, nucleophilic substitution. So we're going to walk through some of those reactions and make sure we're reviewing them, because then you're going to walk through these biochemical pathways and look at the mechanisms. We'll then look at how to regulate these different pathways. We'll look at energetics of the pathways, and we'll look at the whole set of pathways working together. But the first understanding is what's happening on a chemical level. So one of the first reactions that we're looking at here is nucleophilic substitutions. So we'll see substrates like glucose being phosphorylated, and we'll see the reverse of this, the hydrolysis, repeatedly in pathways. So in this case, we have our usual base catalysis here. This is coming over, pull off the proton, make this a better nucleophile. We also have a Lewis acid catalyst, pulling the oxygen minuses toward the magnesium, making the phosphorus feel more electrophilic, so this nucleophile can bind to the phosphorus and break the pi bond. We can then form our tetrahedral intermediate, where this is the O binding to the phosphorus. We have an O minus, an O minus, an O minus, and then ADP, because I don't feel like drawing the whole thing. And we still have our magnesium down here helping stabilize things. Then a pi donation, and we kick off ADP down here. And we've added the phosphate group to the glucose. Now you could easily imagine this reaction going in reverse. Well, not so, you could imagine the diphosphate attacking, or you could imagine water hydrolyzing this when it's the nucleophile. So again, it will be a nucleophilic substitution where the nucleophile attacks and we break a pi bond and then pi donation. So here's another nucleophilic substitution. This is a key step in the beginning of the tricarboxylic acid cycle, the TCA cycle. It's the transferring of the acetyl group right here, which at this point is bound to pantothenic thiol here, so it's a thioester, and it reacts with the vitamin B5 coacetyl-CoA. So this is acetyl-CoA, which is a thiol. So this is attacking, we break the pi bond, and we end up with a tetrahedral intermediate with the O minus, the sulfur, and I'm just going to do this. This is the sulfur with this thiol group on it, and then we have the sulfur that's part of acetyl-CoA. Oops, of CoA, because this is going to be the acetyl group. The carbonyl comes down, kicks off the sulfur, and now we have our acetyl group that got transferred onto the CoA. This is the CoA. So this is called a transesterification, and we'll see it regularly with the sulfurs. We'll see it with esters as well occasionally. Aldols and Clysins. This is an example of an aldol, and we'll see some acid-base catalysis in here, general acid-base. But remember, the first step of an aldol is to always deprotonate the carbon alpha to the carbonyl. So in this case, this aspartate removes that proton, and this goes to form an enolate anion, which will grab that proton, and this will go here, and this will go up here to grab that proton. So we have a whole cascade of transfers here. But really, all we've done is form the enolate anion, or in this case, it's the enol, sorry, S-CoA. These are hydrogens. So we formed the enol, which we know is a nucleophile. We have oxaloacetate, which is the first step. This is the first step of the tricarboxylic acid cycle. And we're going to form citric acid here. So we're going to do this in reverse. This will grab this proton. These electrons will go here. This will come and grab that proton. And then the O will come back to reform the carbonyl. And my nucleophilic carbon here, these electrons will come over here and attack a carbonyl and break that pi bond, which will then go out and grab that extra proton. And we'll see, here's our classic aldol. We've reformed our carbonyl. Then we have our alpha carbon, and we have a beta hydroxy carbonyl. This case, it's a beta hydroxy ester because this is a mixed aldol. If this had been an ester, then it would have been a clisene. So you'll want to go back and refresh the aldols and the clisenes because they'll show back up again in glycolysis as well. And then this is a tautomerization. So in fact, a tautomerization is, we just saw, it's removing a proton. It can be, there are different tautomerizations, but in this case, we're going to see a lot where we remove this proton that is on the alpha to the carbonyl. This is our acidic proton. And so here we have some basic side chain of in my active site. These electrons go here. This comes up and grabs the proton. And again, we formed an enol. So double bond, OH. This is over here. This is the negative form. And then we have the rest of my chain here. Of my glucose 6-phosphate. I'm just going to do this. Right here, we have an OH also. Now, if you look, what I've formed here is an enediol. In the past, you've seen us form an enol, but now I have an enediol. So now, if I remove a proton from here and collapse back down and grab a proton, I would go back to this ketone. But if instead I've removed this proton, then this can come down to form the pi bond here, and this will go out and grab a proton. Looks like we have one over here. So if you want, we could grab that one. So if we take a proton there, and just to be clear, that proton, there is already one hydrogen there. And in the product here now, this is where I have 2 hydrogens. So I've done 2 keto-enol tautomerizations sequentially. I pull off this proton, I form the enol, and then instead of reversing this one, I reverse it down here and I form the ketone back on this site. And this occurs 2 times in glycolysis, these double tautomerizations. But the tautomerizations occur frequently in glycolysis. They occur frequently when you're looking at reactions of sugars, because glucose and fructose are sugars. And then here's our other, and we've seen NADH. NADH is the biological equivalent, so it's a reagent in the system of our hydride reagents. And so in this case, I've got the lone pair on this nitrogen, so there's a big R group down here on this nicotinamide group, but this is the part that's reactive. This will go back this way, and this H minus will be kicked off here, and we'll have formed an H minus here. In this case, if you look ahead, you can see it's going to come over just like we've seen our sodium borohydride and our lithium aluminum hydride, do a nucleophilic addition, to a ketone, forming the alkoxide, which is protonated. Then over here, we formed an aromatic ring. So this is the driving force. This is always stable, but it's got a positive charge. So this is NAD+. This reaction is run forward and backwards in different places in glycolysis in the TCA cycle. The hydride attacks, we form NAD+, but if we have NAD+, we can also do the opposite, which is this oxygen can go down to form a pi bond, kicking off the H-, which attacks here. These electrons come here, and the nitrogen gets its pair back, so it doesn't have a charge, and we form the NADH. And here's the H that used to be attached to the isocitrate, this is part of the TCA cycle, and form oxalosuccinate. And now let me put my carbonyl on here. And the nitrogen is back to its neutral state, so that's part of the driving force for this. We rarely see being able to kick off an H-, but in these biological systems with NAD+ there, you can drive this forward. So those are the main reactions that we're going to see for these pathways. So now I'd like you to just go ahead and get started on trying to walk through some of those pathways and mechanisms.